Hello and welcome to Chapter 8. In Chapter 8 we're going to be introducing the concept of functions. Now you've actually already seen functions, you just may not have realized it yet. An example of a function is y equals 3x minus 7. So this function has an input of x and an output of y. Now with function notations, you won't see the y. What we'll do instead is we'll name the function, we'll call this function f, and our input for that function is x. So we have here a function f of x, which equals 3x minus 7. So these two things are the same thing. Right? Instead of including our y, we just called it a function of x, since that is what y is. It's a function using x. So once again we have our input, x, we have the name of our function, f, and our output we still refer to as y, since y is equal to f of x. So let's get ourselves used to this function notation. We're going to evaluate this function for x equals -2, and we'll also go ahead and try it for x equals 1. So what we do is we plug in our value of x into our function. We're asking f of -2 equals what? Well, plug in -2. We have 3 times -2 minus 7. So f of -2 is equal to -6 minus 7, which means f of -2 is equal to -13. So we had our input, -2, and our output, -13. We can still think of this output, -13, as our y of the function. We just don't see it anymore. So let's try that now with x equals 1. We start with our function f, and we're asking this function, if our input is 1, what is it equal to? We plug in 1, we have 3 times 1 minus 7. So f of 1 equals 3 minus 7, which just means f of 1 is -4. So this is our final piece. Our input is 1, our output is -4. This kind of notation can be helpful when we go to graph this kind of function. Right? This gives us our input and output, or otherwise known as our ordered pair. Right? Our x value of 1 and our y value of -4. So here f of 1 equals -4. We know that that gives us the point 1, -4 on our graph. Here is a verbal representation of our function. We have let function f square the input x and then subtract 1 to obtain the output y. So we know the name of our function is f. Our input will be x. So that's all set. Our output y, that's what f of x is. So we can continue on from there. So let's see what f of x is going to do. It's going to square the input x. So let's take our input and square it. Then we subtract 1. So let's subtract 1 from that. And that will give us the output y. So we have the function f of x equals x squared minus 1. Let's evaluate this for a few different values. I'm going to put this in a table over here, x and y. Our first number, we'll check -1. So f of -1 is -1 squared. -1 is in parentheses, minus 1. Since it's in parentheses, when we square it, that negative also gets squared, and we're left with a +1 minus 1 or 0. So that gives us f of negative 1 equals 0, or our first ordered pair, negative 1, 0. Next, let's plug in 0. Nice simple number to try. So we have f of 0 equals 0 squared minus 1, or 0 minus 1, which just equals negative 1. Therefore, f of 0 equals negative 1. So another point there. We'll try one more. Let's say 1. So we have f of 1 equals 1 squared minus 1, which is just 1 minus 1, equaling 0. So f of 1 equals 0. If we were to then graph this function, we'd have points at negative 1, 0, right here, 0, negative 1, and 1, 0. At first glance, it looks like it might give us a v. However, because we have this square here on the x, we know that this is going to be a parabola. And we can double check that if we plugged in one more point, say the point 2. If I plug in 2, I have 2 squared, which is 4 minus 1, or 3. So 2, 3, and we see that this pattern of a straight line that it might have looked like making a V is actually more of a U shape. So if we connect the dots, we see that we have this parabola. This also helps us see a valuable quality of functions, namely that every function has only one output for every input, which means every time I plug in 1 for x, I always get 0. Every time I plug in 2 for x, I always get 3. There are no other options. What this results in is what we call a vertical line test, which means no matter where I start on my function, if I were to draw a vertical line, I will only pass through my function once, which we see with the parabola. No matter where I go, I only pass through that function one time. If I'm over here, I may not have drawn the rest of the function yet, but I will hit it once. Now I do not have to hit it. Let's take a look at another example. A function again is anything that passes the vertical line test. So no matter where I draw a vertical line, I only hit my function once. On the other hand, something is not a function if I hit the function more than once with my vertical line. So if I have a graph like this, basically a parabola on its side, while I miss the graph completely over here, I only hit it once if I just barely touch the vertex of that graph, but I hit it twice when I go anywhere else. If at any point I hit the function more than once, it is not a function. Which means something like this also fails to be a function. I only hit it once here, but I hit it multiple times here. And if it fails once, it fails to be a function. This means that pretty much all linear functions, functions that are straight lines, will pass the vertical line test, since I only ever hit them once with my vertical line. The only straight line that does not pass the vertical line test is itself a straight line, which means for this vertical line here, which is the equation x equals negative 2, that is not a function. On the other hand, our horizontal lines, right, these nice constant functions here, are functions since I only ever hit them once with my vertical line. So this looks like it is about the equation y equals negative 5.5, or we can call that a function f of x equals 5.5. What we see here is that this is a function of x, but there is no x on the right side of our equation, which means no matter what I plug in for x, it's not going to change what's on the right side here. So I could plug in x equals 4, and I only ever hit negative 5.5. Don't forget your negative sign, as I clearly did. So we try another one. Let's say x equals negative 4. So I go to plug in negative 4 here, but there's no x for me to plug it into, which means I'm just left with that negative 5.5. Alright, so no matter where I go on my x, I always end up on this line, negative 5.5. Those are nice, simple, horizontal functions. Let's consider this ray, for example. So this ray has a set domain and range. The domain stands for all of the values that I can plug into this function. We see that our function starts at the point negative 4, negative 2, and continues on up and to the right from there. So our domain, we'll call D, is all of the possible x values for this function. We start at the x value negative 4 and continue on greater than negative 4. So our domain, our x, is greater than negative 4. Well, it looks like I do hit negative 4, so we'll make sure to put that or equal to option there as well. So x is greater than or equal to negative 4. Our range then is all of the possible y values of our function, everything that we get for f of x. It looks like our function is starting at negative 2 and continuing on up from there, so our range, our y values, are greater or equal to negative 2. So we have our domain and our range of this function. If we have a section of a parabola, as we see here, our domain is still all of our x values, in this case from negative 4 to 4. We can write that as negative 4 is less than or equal to x, which is less than or equal to 4. All of our x values fall in that range between negative 4 and 4. We see x is greater than the negative 4 value, but less than the 4 value in that setup. Our range then is, looks like we go down to 0 on our y's and up to 6. So our range is 0 is less than or equal to y, which is less than or equal to 6. You may also see this written as 0 is less than or equal to f of x, which is less than or equal to 6. Again, y and f of x are generally interchangeable. If, however, our graph has arrows at the end, it does not stop at those points. It continues on. So in this case, our domain with those arrows is, looks like if I continue that arrow, I'm going to go on to the left forever, which means I will eventually get somewhere near in the range of negative infinity. And I'm going to go on to the right forever, which means I'm getting somewhere in the range of positive infinity, which means I can plug in anything I want into this function for x, and I will find a y value. My domain in that case is all real numbers. So all real. Right? If I just write all real, I know I'm talking about the real numbers. So that is my domain. My range, however, it doesn't go below this 0 for y. But it looks like I do go on up forever. So my range in this case is that y will be greater than or equal to 0. since I start at 0 and go up greater than 0 as far as I possibly can. So this is our domain and range for functions. It's just our input, another word for domain, and our output, another word for range. Another way that we can identify domain and range is from the function itself. So if I have f of x equals 1 over x minus 2, I'm asking myself for the domain of that function, what am I allowed to plug in for x? Well, let's try x equals 1. If I plug in 1 for x, I have 1 over 1 minus 2, which is 1 over negative 1, which simplifies to negative 1. That doesn't seem to give us any issues. What about 2? Well, when I plug in f of 2, I have 1 over 2 minus 2, or 1 over 0. 1 over 0 is undefined. That's a problem. So anytime I end up with a 0 in my denominator, my function is no longer defined, which means I cannot use 2 in my domain. My domain then is everything except 2. So x cannot equal 2, but it can equal everything else. So all real numbers except 2, and generally we'll just write our domain then as x cannot equal 2 in this case. What about more simple examples like f of x equals 5x? Well, is there anything that I could plug in for x that would make it be undefined? Well, no. Nothing I plug in for x here will cause any problems. I can plug in negative pi, for example, and it will still give me a number. It may be a very long decimal, but a number nonetheless. So in this case, my domain is all real numbers, because I can plug in anything I want for x. We'll check one other function. Let's say g of x. This time g of x is going to equal the square root of x. Now, is there anything that I can't plug in here that would limit my domain? Well, let's try a couple things. What if I have x equals 0? Well, g of 0 is the square root of 0. I'm asking myself what times itself gives me 0. Well, the only thing that does that is 0. So I run into no problems here. What about, say, 1? Well, g of 1 is the square root of 1, which is 1. Again, no issues. How about negative 1? Well, g of negative 1 is the square root of negative 1. I don't know that. There's no number that multiplies by itself to give me negative 1. So in this case, again, we cannot use negative 1 for the domain. Now, I know some of you may be thinking, hey, isn't negative 1 an imaginary number, I? Yes, it is, but we'd like to stick to the real numbers for now, without introducing a new number system. So if you know what I is, don't worry about it for now. We're just going to focus on the real numbers. And there is no real number solution to the square root of negative 1, so we cannot include negatives in our domain, which means our domain for the square root of x is greater than or equal to 0. Since I can plug in 0 and everything bigger than it, all of those positive numbers, but I can't plug in anything negative. Let's focus in more on linear functions. So, for example, our general linear function comes in the form f of x. Again, our name of the function is f. Our input will be x. And for linear functions, we have the form mx plus b. You may recognize this. This is our linear equation, y equals mx plus b, where m is the slope of your equation and b is the y value of your y-intercept. All we've done is replaced y with its new name, a function of x. I'll slowly be introducing you to all of the vocabulary for this. We've talked about how x is our input in our function, and y, or f of x, is our output. Another word for that is x, instead of input, can also be called our independent variable. It is independent because it gets to do whatever it wants. We can plug in usually whatever we want in for x, and our dependent variable then is y, or f of x, because it depends on what x is to get its value. Linear functions will always fit this form. So if I have another linear function here, we'll give it a new name, say g of x. And g of x is 4 minus 3x. Now it may not be in the same order, but we see here our m value is the coefficient of our x term, -3. Our b value is 4. It fits this form, so g of x is a linear function. We'll try another one, say h of x. H of x is 8, just plain old 8. And just as we saw in our previous example, this will be a horizontal line at y equals 8, or h of x equals 8, which is a straight line and thus a linear function. In this case, 8 is our b value, and since we have no x value, we can assume that our slope is 0, since 0 times x is 0, right? So we're adding nothing to that 8. So yep, that is a linear function. We'll try one more function. We'll call this one j of x, and j of x is 2x squared plus 8. Now it almost looks like it's in the same format as our linear function, but we have this exponent here. Anytime our x variable has an exponent other than 1, right, which is the assumed exponent here, it is not a linear function. So no go, that is not linear. We're just going to be focusing on our linear functions. So if we focus in on this function g of x, we know it's linear. It has an x variable with an exponent of 1. It may not be in the form that we're used to, so we can rewrite that, if that helps, as g of x equals -3x plus 4, keeping the sign with those corresponding numbers. 3 was negative here, it better stay negative. 4 is positive here, it better stay positive. You're familiar with how to graph these functions, but we'll go over that one more time so that we see that again in terms of g of x. We have our table of x and y values. You can plug in some x values into our independent variable x, because it gets to be whatever it wants. And then depending on what x is, our dependent variable y will have its own value. So let's say I plug in 1 for x. Plugging in 1 for x gives us -3 times 1 plus 4, which is just -3 plus 4, or 1. So we have the point 1, 1. From there we can plug in, say, 2. If I plug in 2, g of 2 is -3 times 2 plus 4, or -6 plus 4, and we're left with a -2. For linear functions, all we need are 2 points, since 2 points cause a straight line. So we graph our 2 points at 1, 1, and 2, -2, right here. And we connect those 2 points to make our line. And that's about as straight of a line as I can draw. So we have here our linear function. We know it's a function because it passes that vertical line test, and it's a nice straight line or as straight as I can draw it, which makes it a linear function. Let's consider this table. So the table here estimates the sales of green building material in billions of dollars, which means that in the year 2010 there were $65 billion worth of sales of green building materials. 2012 had $75 billion worth of sales. If we want to create a scatter plot of this, we can draw our graph. And now we have to decide, where does years go and where do sales go? Now generally, when we're trying to decide this, time, or years in this case, will always be our independent variable because no one can change time. It is constant. What does change, or what depends on what year we're looking at, is our sales. So sales goes up top for our y-axis, and years will be our x-axis, our independent and our dependent variables. One little trick that you'll see happen relatively often is, instead of going all the way out to 2010 onto our x-axis, we're just going to call 2010 our 0 year. So right at 0 is 2010. That means 1 is 2011, 2 is 2012, and 3 is 2013. Another little trick that you will see sometimes in graphs is these double bars here at the bottom at an angle. Those double bars basically means there is a break in the graph so that they don't draw everything below it. Since we're going to be skipping ahead here for sales, right, generally we won't redefine our 0 for sales, or our dependent variable. So we're coming up here to 65. We'll go and start at 60, and each mark after that will be 5 more. So 60, 65, 70, 75, and 80. If we're going to plot this, we're going to again start at 0 for 2010 and come up to 65 for our sales and put a point. For 2011 we're at 1, sales is at 70, year 2 at 75, and year 3, or 2013, at year 80. Just leaving it in this form with those 4 points. This is called a scatter plot because it just has the 4 points. It is a plot, looks like of scattered points, hence scatter plot. Let's ask this question now. What was the annual increase in sales each year? Relatively simple to see since each increment here is 1 year. So in 1 year, from 2010 to 2011, we went from 65 to 70, or an annual increase of $5 billion. So our annual increase in sales each year is $5 billion. Another way we can think about this is asking us what is our rate of change, or another word, slope. The slope of this graph, you take your change in your y values over change in your x values, or in this case sales over years. We have y2 minus y1 over x2 minus x1. That is our formula. So in this case we take any 2 points. Let's go ahead and take 2011 and 2013, make it interesting. So we have our y2 value of 80 minus our y1 value of 70 over x2 2013 minus x value 2011. So we end up with 10 over 2, which simplifies to 5. We get our $5 billion there. So what then is the formula for this function f of x? Well, we start with f of x equals, let's see here, we know it's supposed to be in the form of mx plus b, where m is our slope. Oh yeah, that was our annual increase. So 5x plus b, which was our y value of the y-intercept. If we come over here, we hit the y-axis now at 65 billion, since we reset our 2010 to be year 0, and each year after that to be 1, 2, 3. So our y value of our y-intercept is 65 billion, and since all of this is in billions of dollars, we just have 65. So f of x equals 5x plus 65, all of those in billions of dollars. This now then is our model for this scenario. We can then use that formula to estimate future sales in 2014. We don't have 2014 on this graph, but we can plug it in, since that is our independent variable, and find our dependent variable, sales. So f of 2014, now again, remember we rescaled this, so that was 0, year 1, 2, 3, so 2014 must be year 4. So we're finding f of 4. Plug in 4 everywhere you see x, so we have 5 times 4 plus 65. So f of 4 is 20 plus 65. Therefore, f of 4 is 85. 5 more than the previous year, which is exactly what we would expect with an annual increase of 5. So let's quiz yourself a little bit. Take this table for example. I'm driving along the highway, and at 0 hours, so at the beginning of my trip, I'm driving 70 miles per hour. At 1 hour into my driving, I'm still driving at 70 miles per hour. So on and so forth, right? At 5 hours into my driving, I'm still going 70 miles an hour. First, ask yourself, is this a function? So functions have only one output for every input. So let's check here. Each of these numbers are unique, 1, 2, 3, 4, 5, all the way down, and they only have one number associated with them. So yes, this is a function. Next, let's ask ourselves, what is the equation for this function? So we have our f of x, and then it needs to fit into some form. Now, it seems like I'm going at a pretty constant rate here, staying at 70, which most likely means, right, we have this horizontal line at 70. That's a linear equation, so we should be fitting into the form mx plus b. Well, in this case, m, remember that is our change, right, our slope, and b is our y value of our y-intercept. Well, what is our change in this case? I don't go up from left to right. I don't go down from left to right. My speed is not changing. So there is no change. We have 0 change times our x value plus b, our y value of 70. Now this is kind of a weird way to write our function, so let's simplify that. Right? We don't put 0x here because 0 times x is 0, so this is just f of x equals 70. So regardless of what time I'm at, right, whether I'm at 2 hours into my drive or 5 hours into my drive, my speed is always the same at 70. So this is a function of my speed given how long I've been driving. Let's check with this now. We have these set of x values and y values. Is this a function? Well, let's check. Each x value should have its own y value. None of the y values are repeating, but we see here we have a set of x values that repeat and another set of x values that repeat. Well, as long as those x's have the same y value, we're okay. Here 0 is -1, but here 0 is 4. It gives me a different output. So this is not a function, and we would not be able to write this as a function. So this here is a little misleading, right? It is not a function of x. The last thing we're going to take a look at is the midpoint formula. The midpoint lets us find a point in the middle of two other points. If I have a point here on my graph and a point here on my graph, the midpoint formula will let me use the x and y values of those 2 points to find the point exactly in the middle of those two. So if this first point is x1, y1, and this second point is x2, y2, with our little commas here, we can use these to find our midpoint. The midpoint formula then is x1 plus x2 over 2 and y1 plus y2 over 2. Now this formula comes in the form of a point because we want a point. This side here will give us our x value, and this piece here will give us our y value. This equation should look similar to the average formula. Right? When you add two values together and divide by how many numbers you added together, it gives you the average. What we're really doing then is finding the average of our x values and the average of our y values, and in doing so, that gives us the point right in the middle of those two. So let's say I want to find the midpoint between these 2 points, -3 and -2 for my first point, and 4, 1. So the point halfway between those 2 points, we set that up into our midpoint formula. You have your x1, -3, plus your x2, 4. Just finding the average of those two values, throw it over 2. Our y values, -2 plus 1, all over 2. So simplify that. -3 plus 4 is 1 over 2. -2 plus 1 is -1 over 2. And look at that. We have our midpoint between those 2 points. At 1/2, -1/2. So our x value and our y value. Again, just to reiterate, that is our independent variable x and our dependent variable y. So to recap, we took equations like y equals 2x plus 5, and we renamed them as functions. Give them a name f with their input x, and then the actual equation that that function is equal to. So this is a function of x, and this is that function of x, 2x plus 5. To evaluate functions, you just plug in what value you want your independent variable to be, say 1, and you have 2 times 1 plus 5, or 7, evaluating your function. This particular function is a linear function because it comes in the form mx plus b, with a slope, a y value for your y-intercept, and an x with an exponent of 1. We also have other functions that give us lines, but with a different name usually. This g of x equals 3. This is called a constant function because it is constantly 3, or constantly whatever number that function is equal to. Finally, the midpoint formula, x1 plus x2 over 2 and y1 plus y2 over 2 gives you the average of your x values, the average of your y values, and spits out the point exactly in the middle of those 2 points. Okay, so that completes Chapter 8 and your final video of this class. I hope you have enjoyed it. And don't forget to go and complete your homework and quiz over Chapter 8, and then start studying for that final exam. Have a wonderful rest of the semester.